welcome back to another fun episode of Exponential Regressions. We are going to talk about that today. And regressions for exponential functions are really similar to regressions for polynomial functions. The steps that we use to do them are identical. Step 1, we're still going to plug in that table on Desmos. Step 2, we are still going to enter the regression equation using x1 and y1 rather than x and y. And we're going to use that squiggle rather than the equal sign. And then Desmos is going to spit out some a and b values for us that we're going to insert back into the original equation. So to kick things off, we are going to start with this example here. And we have the population of Canada from 1871 to 1971 shown in this table below. And we want to graph the data given on the graph and then draw in a curve of best fit. So we're going to go ahead and do that. Remember that when we're graphing anything, we need to make sure that we have a couple of key things. So thing number 1 that we need to have is we need to label our axes. So we have to figure out what's independent, what's dependent. The year is independent, so that goes on the the x-axis. Which means the population is going to depend on the year, and that is going to go on the y-axis. We also need to have a meaningful title. Usually we want to address the labels of the x and y axes as we do so. So we could call the graph something like Canada's population over time. All right. The next thing that we need to do is we need to draw, or label our scale. Okay, so maybe I'll pick a different color to do this. For our year, we start in 1871 and we go up to all the way to 1971. Obviously, we don't want to start the graph off at 0, but that's normally how graphs do start. So what we do is we draw this break in the graph, which is equivalent to this like lightning-y squiggle line. That indicates that the graph has kind of been folded in, and then we can start wherever the heck we want. So we're going to start in 1871 here, because that's the first one. And it's going up by tens every year, so we might as well go up by tens as well. So 10, 1, 90, 1, 11, 21, 31, 41, 51, 61, 71. Okay, so I might label every couple away just so that I know which one I go down. So 81, 91, 1901, 11, 21, 19, 31, 41, 51, 19, 61. All right. Now, our y-axis has all these values in the millions. So what I might want to do is, instead of writing out all those extra zeros, I could put millions as my units for my y-axis there. And then I could go ahead and then just use smaller numbers. So I'm going from essentially 2 million all the way up to 22 million. So don't have a ton of room. Maybe I'll go up by like 2.5 million at a time. Seems somewhat reasonable. And making sure that my scale's consistent, in that way all the ticks are evenly spread apart. So 2.5, 5 million, 12.5, no, 7.5, 10 million, 12.5, 15 million, 15.5, 20 million. Nope, I spread those out too far. Let me try it again to make sure they're spread out a little bit closer. 2.5, 5, 7.5, 10, 12.5, 15, 17.5, 22. Okay. So this is going to be my 5 mil. This is going to be my 10, my 15, my 20. means my 2.5, my 7.5, my 12.5, my 17.5, my 22.5. And again, realistically, your scale can look different than mine. It doesn't have to be bang on, but whenever we're drawing any sort of graph, we want to use the space available to us. So we don't want to squish up a small little graph up into the corner. We don't want anything like this because that's not really meaningful to us. And we want to spread it out. And we want to try and use as much space as possible by keeping our scales consistent at the same time. We're going to go ahead and it says to plot all the data given. So we're actually going to be drawing a scatter plot, and then we're going to make a curve of best fit. So here we have, at 1871, we have 2.44 essentially million. 81, we have about 3.23. Then we have 3.74. Then we have 5.42. Then we have 7.22. We have 8.8. We have 10.3. We have 11.5. We have 14. We have 18. That takes a bit of a leap. And then we have 21. All right. And of course, we're just doing our best to get our data points in there. It doesn't have to be perfect, but it should represent the same kind of shape. And we are now drawing in a curve of best fit. Okay. So, of course, we don't have to hit all the dots, but we are drawing some sort of curve. There shouldn't be any lumps and bumps along the way. If that is the case, you should erase what you did and try it again. Okay. What we are doing next is we are going to determine the exponential regression to model the data, and we're going to keep 6 decimal places. Whoop, whoop. So I took the liberty of entering the data into my table already in Desmos. Oops. And maybe I'll make Desmos a little bit bigger here. And I'm going to go ahead and I'm going to change my scale just so we could see what's going on here. So I'm going to maybe go from, 1850 to 2000 on my X scale. And because I'm in the millions here, maybe I'll hit 0 for the y-axis and I'll go all the way up until, 22.5 million. I kind of get an image of what my data looks like. And when I enter the regression equation, so I have y1, my squiggle, times a, times b, to the power of x1. And when I take a peek at this, here is what I get. Okay. So I have, my y is equal to, and let's just keep 6 significant figures rather than decimal places here because our a value is getting pretty small here. So we have 0 point, and this is scientific notation to the power of -10. That means we're moving our decimal place over 10 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we write the rest of the number. Okay, that's our A value. Our B value is much more reasonable at 1.02009. And it's to the power of x. Okay. Notice that when we were doing our regression equation, we are using y and x when we're writing our final answer. We're not using y1 and x1. That is a trick that we use Desmos, so that the Desmos knows what we are talking about, what data to pull from. Is not something we should have in our final answers. And same with, we're having an equal sign with, rather than that squiggle. That squiggle is, again, only for Desmos. Okay. All right, assuming that the population growth continued at the same rate to 2011, estimate that population. By all means, let's do that. So we should have x is equal to 2011. We're trying to solve for y here. So x is equal to 2011. And we are finding that intersection. And holy Toledo's, check that out. So our y value would be 4, and then since we have scientific notation, we are moving our decimal to the right 7 times. So 8, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Beautiful. So our population that we're estimating here is a whopping 48,166,000 people by 2011. All right, and then the last question here, it says, at what year would the population of Canada be predicted to reach 50 million? Well, that's when our y is 50 million. And we are looking for our x. So we plug that into Desmos. Y is equal to 50 million. And we find that out to be 2012, oops, what's the point here? 0.89 or 879, which we know happens in the year 2012. All right. So hopefully this doesn't seem all too new so far. Realistically, exponential regressions, logarithmic regressions that we'll eventually do, any sort of regression is done using the same basic steps. So hopefully this should seem fairly familiar. We just have a new shape of our graph. All right. Next, we are going to talk about the exponential growth function. And we actually just saw an example of that. So I'm going to kind of shut down Desmos here a little bit. And we're going to give this a little bit of a definition. So an exponential growth function is an exponential function whose y values increase as you move left to right along the x-axis. Move left to right along the x-axis. All right. So that is our formula that we know. We know y is equal to a times b to the power of x. We know that a cannot equal to 0. When we have a growth function, that means it's continually increasing, which means that our b value is going to be greater than 1. And you could recall back from 8.1 when we talked about if b is greater than 1, we are going to have an increasing graph, which represents growth, right? So in an exponential growth function, the initial value can be represented by a, and the rate in which it increases per 1 year can be represented by the b value. So we are going to take a look at this next example. So imagine you have a piece of paper in front of you. You probably do, it's your notes paper, but we're going to be folding this imaginary paper you have. Create an exponential function that represents how the number of times you fold a piece of paper in half affects the number of layers of that paper. So we are going to define a couple of variables here. So why don't we say that x is our independent variable, and what our independent variable is the number of times we fold the paper. Number of times we fold the paper in half. And y, our dependent variable, will be the number of layers of paper. All right, so we aren't given any data here, and we have to figure out an exponential function, which means we have to come up with our own table of values. Okay, and we're going to start and go ahead and make a table of values. We'll have our x, Maybe I'll write the number of folds here. And then this one will be your number of layers. Well, what happens when you fold the paper 0 times? How many layers of paper do you have? Just have the one. Now imagine taking that paper and folding it right in half. I don't care, hot dog, hamburger, you choose. If you do one fold, you now have 2 layers of paper. Well, what if you take that hamburger, let's say, and you fold it in half? So you have 2 folds now in your paper. Well, now you'll have 4 layers. What if you have 3 folds? Well, now you'll have 8. And we can continue this realistically as much as we want. Although I did see a Mythbusters video that says you could only fold a paper, like, I can't remember if it was 7 times. They had a whole bunch of steamrollers and things involved. It looked intense. Once you're done with this, I highly recommend watching it. Anywho, that's what we get. We could make this as big as we want in terms of our table, but as long as we have 3 points, that's all we really need to do the regression here. So we're going to take all this data, and we're going to plug it into our Desmos. I'm going to clear everything we had before. And I'm going to start plugging in this table. So we go to table, 0, 1, 2, 3, 4, 5. We have 1, 2, 4, 8, 16, 32. Ooh, 32. Okay. And just make sure you plug in everything correctly, because you wouldn't want to lose any silly marks. And here we go. So from here, we are going to plug in our regression equation for our exponential function. So we have y1, the squiggle, a times b to the power of x1. And here we get an a value of 1 and a b value of 2. So going back to our work here, if you're ever asked, hey, could you show your work in doing everything on your paper, especially on a provincial exam, if you ever end up writing one of those, the only work that you need to show is that you say, okay, here's my table of values. Here is what I plugged in to Desmos. And then that is all. From there, you can go ahead and plug in the value. So y is equal to 1 times 2 to the power of x. This is technically not fully simplified because multiplying something by 1 does nothing to my final end result. So I should have y is equal to 2 to the power of x. And that would be my final answer here. Alrighty. Now that we've talked about exponential growth functions, we're going to look at an example of exponential decay. So essentially, the opposite. And here we've got this chick named Sonia, and she did an experiment to determine the cooling curve of water. She placed hot water into a glass beaker, then she recorded the temperature of the water in the cup as it cooled over time. This is her data. We want to construct a scatter plot to display the data, and we want to draw in a curve of best fit. Alright, for Sonia, anything. We're going to start by labeling our axes. Time is going to be our independent variable, so it's going to go on our x-axis, and we have the units for time in minutes. On our y-axis, we have temperature, and the units for temperature is in degrees Celsius, because we assume that Sonia is a big fan of the metric system. Then we also need a title, something meaningful that ties the two axes together, so we could say the temperature of water over time. Alright, now we need to figure out some sort of scale here. Okay, so if we're looking at our x-axis, we have to go from 0 to 40 at a bare minimum here. So 0, 40. Sometimes when they're even numbers, I like to put one at the beginning, one at the end, and then just split it halfway down the middle and keep on breaking it up that way. So that's 20, which makes this 10 and this 30. Oops. and this 30, which would make this 5, that 15, 25, 35. And that kind of covers all my bases there. And for my temperature, I'm starting off at 0 here, and I want to get as high as 80 degrees. So I might do the same thing. I might kind of guess and check here. I don't know, maybe I'll go by 10s, 10, 20, 30, 40, 50, 60, 70, 80. That'll do. And of course, I'll write in my scale. So 10, 20, 30, 40, 50, 60, 70, 80. All right, now it's scatter plot time. Whoop, whoop. All right, at time of 0, I have a temperature of 80 degrees Celsius, so there's my point. At time of 5, I'm at 69 degrees Celsius. At time is 10, I'm at 61. At time is 20, I'm at 45. At time is 30, I'm at 34. At time is 40, I am at 26. And I am going to draw in a curve of best fit. And again, it doesn't have to hit all the dots perfectly. It shouldn't have that bump in there though. So let's get rid of that. Okay, we're not connecting the dots, we're drawing in a line of best fit, which means we're getting as close as possible to drawing something nice and smooth. Okay. Remember, we are not connecting the dots. And lastly, remember that on one side, it makes sense to draw an arrow, right? Time is going to continue on in the positive direction after 40 minutes. Time doesn't stop. But time is not going to backtrack past 0. We're not going to have time or a temperature prior to starting the experiment, so it doesn't make sense to draw an arrow on that side. All right. Next, we want to determine the equation of the exponential regression function that models that data. So we're going to go back to our Desmos here. We are going to get a new table involved and start plugging in our data. So we have 0, 5, 10, 20, 30, 40. And on the Y, we have 80, 69, 61, 45, 34, and 26. And of course, we're going to double check that we plugged in everything properly because we don't want to lose any silly mistakes by accident. I'm going to change my scale in which I could see all these things so that it's appropriate for what I want. And here I go. I'm going to put in my regression equation. So my y1, my squiggle, my a, my b to the power of x1. And I should get something along these lines here. So I end up with y is equal to 79.98 times 0.97 to the power of x. Remembering that I use my full y and my full x in my equation rather than y1 and x1, as well as an equal sign rather than the squiggle. The squiggle, the x1, and the y1 are reserved for Desmos only. All right. Next, what we want to do, we want to estimate the temperature of water 15 minutes after the experiment began. So our time, our x value is 15. And we can go ahead and do that by plugging x is equal to 15 into the graph, finding that point of intersection, and we want to round it to our nearest degrees. So y will be 52 degrees Celsius. And next it says, estimate when the water reached a temperature of 30 degrees. Round your answer to the nearest minute. So at this point, we have our y is equal to 30. And look at that. We have it at 34.621 minutes. So when y is equal to 30 degrees Celsius, our x is rounded to 35 minutes. Again, this shouldn't be too new to you. It should feel pretty similar to our previous unit. And hopefully you're feeling pretty good about that. All right, last section is, I know we just looked at an example of this, but let's define what we're talking about now that we've seen it in real life. So we have, shimmy down Desmos for a little, the exponential decay function. So it's an exponential function, believe it or not. Whose y values decrease as you move from left to right along the x-axis. Okay. And we talked about decreasing functions. So if we're looking at our exponential function here, y is equal to a times b to the power of x, we know always that a can't equal to 0, but we know that we end up with a decreasing function when we have a b value that's greater than 0, but still less than 1. So b is greater than 0, but less than 1. All right. In an exponential decay function, the initial value could be represented by a, which makes sense because a is the idea of the y-intercept. And usually if we have something decaying, it's over a period of time. So the initial value is when that time is 0. So the y-intercept makes perfect sense. And the rate in which it increases per 1 unit can be represented by b. So if you think about it, it still says increases here, right? Think back to like finance when we were talking about that. The rate at which it decreases can be thought of 100% minus your decrease. And then that gives you the rate at which it increases, which is still going to be our b value here. So we're going to look at it one more example, then we're going to call it a day. It's going to be a great day. And we're going to think back to that standard sheet of paper. So that paper that you have in front of you that's 8.5 inch by 11 inch. Ooh, baby. Nice sheet of paper. So we're going to create an exponential function that represents how the number of times you fold a piece of paper in half affects the surface area. Okay, so we have to introduce some variables. We've got to come up with some data, plug it into a table, plug it into Desmos, get a regression equation. Oh, and we know how to do all of that. We're just a bunch of smarties, hey? So x, in this case, is our independent variable, as always, and that's going to be the number of times we fold our paper in half. Fold our paper in half. And y is going to be the surface area of the top of the paper. Right, so when we fold it, we're only looking at the surface area or just the area at the very top of that sheet of paper. Okay, so we are going to create a table. So we have the number of folds, and then we have the surface area here. Okay. When you fold a piece of paper, or before you even fold a piece of paper, 0 folds, what is the surface area? Well, if our sheet of paper is 8.5 inch by 11 inch, that means it's a rectangle, so we could length times width the heck out of this. And we should get 93.5. We could note that our surface area should be in inches squared, but realistically, we don't have any follow-up questions here, and we don't have to put units in our equation. Something just to keep in mind in case there ever were follow-up questions. Anywho, once we fold that, what happens to our surface area? Well, it cuts right in half. So we end up with a surface area of 46.75. And if we fold it again, cuts down in half again. So we get 23.375. And we could do this all day. Yeah, this could just continue on forever. We could do as many as we want. Again, we only need to have 3 points. So realistically, after you got to 2 folds, you could have stopped. But just for the sake of showing you the show does in fact go on, I figured I might as well. We're going to reopen Desmos here. Doop-a-doop, doop-a-de-doop, doop-doop-doop-doop. We're going to open up a table. We're going to plug in all these beautiful values. Oh, so nice, so nice. Oops, where'd that 8 come from? 3, 4, 5. And we're going to plug in all of the values here. 46.75, 23.375, 11.6875, 5.84375, 2.921875. Oh, oops. 5 point. Now we go 2.921875. I'm double checking that I plug these in correctly, because that's the worst when you got all the correct work and then you just made a little boo-boo. Alright, now we're going to regress the heck out of this thing. Plugging in our regression equation, using our x1s, our y1s, all of that. And we're going to show our work back on our sheet. And our work, all we have to show is exactly what we did in Desmos here. And now we spit out our final answer. So we have y is equal to our a, and our a value is 93.5, times b, which is 0.5, to the power of x. Right? Which makes sense. And remember, if we look back over here, our initial value could be represented by a. And here our initial value is the initial surface area we started with when we had 0 folds. That's 93.5. And the amount that it increases by can be represented by b. And you might be thinking, well, it increases or decreases by 50%. You could also think of it as increasing by 50%. Right? When you multiply it by 0.5, that's multiplying by a half. So it's getting 50% smaller when it's increasing by 50% as well. So nice little connection there. All right, that's actually it for today's lesson. You have some homework to follow. You've got 4 questions to do. You could do it. I believe in you. All the answers are posted online. Otherwise, take care.